Hello. Hello and welcome to this video. In this video, we will talk about segment trees. We have seen the theory in previous video. So we will do the implementation in this video. And there is an important decision I have made regarding this playlist. Okay. So let's look at how does it work. So we have an array. We put in values 1, 3, 5, 7, 9, 11. We find out the size of array, okay, and we call function stcreate, stbuild, and then we have stquery, and we have stupdate should also be there. Yeah, stupdate should is there. Oops, there is some mistake here. Okay, we have stupdate also, and stquery again after the update. So first we see what is stcreate. St stands for segment tree, all right. So let's go and look at stcreate. So what it does is it mallocs size of st. So st is basically our segment tree structure. It contains n, that is how many elements are in the array, and basically an int pointer tree. So when it creates the segment tree, it takes input n and sets n of the segment tree and allocates 4 times size the number of elements, and that multiplied by size of int, that many bytes you allocate, and you calloc those. Okay, calloc we do so that the nodes are set to 0. Now you saw that we call stbuild. Okay, so stbuild is called with the array, with a segment tree and the array pointer. Now what we do here is we call build from stbuild. Okay, this is a wrapper call simply because there are certain values we want to pass which are hard coded, but we don't receive them. So we send stn array which we receive to build, then we send 1, 0, st and -1. That is, this is our node variable in the function signature. This is start and this is the end of the array. So if you look, it is fairly straightforward function. If we see that start is equal to n, we set the tree node is equal to array start. Okay, and we return it. Else what we do is we find mid. Okay, and after finding the mid, we call build recursively. So in build, we send one half of the array to one call and the second half to the other call, and we multiply node by 2 as well. So you see, what we do is we send one half of the array to one function and the other half to the other function, and the node is increased by 2 into node and 2 into node plus 1. And then finally we set the node variable of the node position of the tree, and that is equal to the position 2 into node plus position of 2 into node plus 1, because that's what we discussed in the theory side of it. If you have not watched the theory video, you should definitely go and watch the theory video, otherwise you will not understand what I'm talking about. Now let's look at query first. Okay, query is similar. It receives the segment tree pointer. It receives int for lookup and int for return. Okay, yeah. So let's see what is R. Okay, so R is also an integer, L is also an integer, and it returns what the query returns. So what query does is it takes the segment tree, it takes the st segment tree, takes the node, takes the start is 0 and end is n -1, and L and R are 2 more parameters. So if you look at this query stuff, then query sends 3 values: segment tree, L and R. So segment tree, L and R come from the query. So L and R is the left-hand position of the slice and R is the right-hand position of the slice. So here, for example, slice 1, 3 is required. Here range 0, 5, slice or range. Here range 2, 4 is required, and we want the sum of that. So if you look at now query function, what it does is it receives the ST structure, node, start, end, and the left half of the slice, left index of the slice and right index of the slice. So if R is less than start or end is less than 1, L, then we return 0, okay? Because that is our invalid case. Now if L is less than equal to start and end is less than equal to 1, we return ST3 node. And then we compute the sum, we compute the mid element, okay? And like previous one, the logic which we had discussed, we do that recursively. ST2 into node, start, mid, L and R, ST2 into node plus 1 and mid plus 1 and L and R. So we recursively call the other segments. So eventually, when you see that this will go on increasing and decreasing because mid will change here all the time. Okay, L and R will remain constant here. And since mid will change, these conditions will start changing. Okay. Now we look at the update, that what update does. So like range, we have ST, which receives 3 parameters, ST and the position and the value. Okay. So let's see what update does. So update receives the index and the value. So in here we have index is equal to 3 and value is equal to 6. Okay. Now it sends to the update function 1, 0, the length of the array always, and index and value. Okay. So here we receive node, start, end, index and value. And if we see that if start is equal to end, then we set the node to the node with the value val. Again, we compute the mid of the array, and if index is less than mid, then we update the tree. We recursively call the tree to update with node being set to into node, and the end changes to mid, and that is the left half of the array. Else, what we do is we update the node to 2 into node plus 1 and starts to mid plus 1. And finally, what we do is we set the ST3 node to ST3 node 2 into node plus ST3 2 into node plus 1. And that's how we recursively solve it. So let's run this and we see how it works. So we do build. Okay. Now one thing is here to be noticed is what we call this. Okay. So since it is recursion based, what we should do is, if you want to really run this program on large output, then you should do a -O2 in that, so that it can optimize for tail recursion. Okay. If you don't do that, what will happen is that your code may not handle the what we call unlimited depth of recursion. I have talked about tail recursion a lot in earlier videos also. So similarly, we should optimize the code for tail recursion in this case by passing -O2. Now let's see if it is really possible to do the tail recursion. So I don't think we need tail recursion in this case. The reason is that it's a binary tree, okay? So even if you go to 10 levels, that is 10 recursive calls, that is 2 to the power 10 elements you can match, okay? And if you have, say, 30 levels, then you have what we call 4 billion elements roughly. Not 4 billion, 2 power 30 would be 1 billion. 1 billion elements can be stored in, or rather queried with 30 recursive calls. So, and typically that the memory consumption, if you look at that level, is then 4 times that it will consume roughly. So say this is 1 GB, that is 2 to the power 30, then it would consume roughly 4 just 16 GB RAM it will consume. Okay, and that's quite a lot of memory for one machine. And if you increase one more level, then that will be double. Okay, so 16 to the 32 GB straight up memory consumption would be there. So it cannot have a lot of depth on a single machine. That's the point I'm making. And therefore, -02 is kind of not needed. Okay, you usually build a production code with -02, but it is not needed in this particular case, in the sense that to achieve tail recursion, we don't need to do that. Okay, so of course, production code will have -02 flag while compilation, but that does not mean that it requires tail recursion. The other reason why we will not be able to do tail recursion is that this query relies on the return value of this. So this call will rely on the return value from this call, and therefore it will not be able to perform tail recursion. Okay? It cannot be done. So you look at the output, and output is what we have expected by computing the manually the range of 1 to 3, 0 to 5. So if you look at the range 1 to 3, so 3, 5, 8, and 7, 15, and 0 to 5 is 4, 5, 9, 9, 7, 16, 9, 25, 11, 36. So with this, we come to the end of this video, but the important discussion which I wanted to talk about is that this is the last video of this playlist. You would ask me why we are ending the playlist. The reason is that I think that C++ is what we should writing code in data structure code. The reason is in the competitive programming, not every what you call competitive programming website allows you to code in C. For example, Topcoder does not allow you to code in C. The second thing is that C code is so verbose. For example, you don't have hash map, so you'll have to always write your hash map, linked list, vectors. You have to implement everything on your own. So the timing constraint is a bit problematic in context because you have to submit the solution fast. So C++ is what we are going to use. I could have used Rust, but the problem is ICPC does not even support Rust right now. So C++ is what we'll go with, and we will study in C++. I wanted to avoid C++. The reason is it's quite complex language. You will see when I'll make the next video on C++. So a new playlist will be started on C++ programming, and in the next video, I'll show you the basics of C++. We'll talk about the language, and we will talk about what is good and bad about it, and also that how it can help with competitive programming. So the only thing we need in C++ is a Bignum library, and that is the extra that standard library does not provide, and we will be able to use a lot of standard library stuff. So it will be a long playlist because C++ is quite complicated and we will have to cover a lot of ground. So I'll see you in the next video with new code. And it's not that we are ending data structure forever. Once C++ is done, we will do the data structure again. So stay tuned for that. And thanks a lot for watching the video. Happy programming. I'll see you in the next one.